Hello everyone, thanks Martin for the intro. So in this talk I will be talking about our work which got accepted to PETS 2025. So it's high throughput secure multi-party computation with an honest majority in various network settings. So this is a collaborative work with Christopher and George Call from TU Munich, Hossein from Robert Bosch, and Yongqing Wang and Murli Annavaram from USC. So first question is like the typical question, like how many of you doesn't know MPC? Everyone knows MPC or you don't? No, I know. So everyone knows MPC, right? So I can quickly skim through the slides. So secure multi-party computation, there are n parties with their own private inputs and they want to basically compute a joint function on their inputs, and we mainly have two main goals of correctness and privacy. So where we want the function computation to correctly output the function output, and privacy is like nothing more than what what can be inferred from their input and the function output. So nothing more than that should be revealed. So that's the notion of privacy. And we mainly focus on the case where we have some corruption among the set of parties and we want to have these properties retained even in the face of corruptions. One of the most exciting area within MPC is the secure outsourcing paradigm, and this is mainly popular because it can actually solve the issue of MPC for a large population. And how it is being done? We basically outsource the computation to a set of powerful servers. That's mainly because like most of the clients they may not have enough computational resources to carry out the computation. So like among the clients we will choose a subset of parties and they will be assigned as like the computation parties, and the computation roles are kind of like outsourced to them. And the main goal is the average end users benefit because they don't have the resources, but at the same time they can avail the result of the computation. And it, like I mentioned, it solves the issue for a large population. And of course, like it's not like okay, if I have 100 people and they are doing a multi-party computation versus like a subset of like let's say 3, 4 or 5 parties. So of course the trust will be entrusted to this small committee, but at the same time we can assume like okay, not all are getting corrupted and we can instantiate the setting with us like the right MPC protocol. And in the literature mostly it's this setting is focused with 2, 3 and 4 computational parties, even though there are results with 5 and more, but most of the time like the focus is on this many parties. In 2 parties we will tolerate up to 1 corruption, and even in 3 party and 4 party we mainly tolerate up to 1 corruption because of the practical efficiency. Actually these 3 settings are uh, if you see the like MPC corruption threshold, first one the 2 party setting has like 1 corruption, so it's a dishonest majority, whereas 3 party 1 corruption is the starting point of honest majority, and 4 party 1 corruption is actually a super honest majority, like you have 1/3 corruption. So these 3 settings actually are the starting points of the respective setting, and that's I think that's why they are mainly like focused in the literature. And the desired properties are privacy and efficiency from this kind of a setup. And as you know, like MPC has various dimensions, like it has so many orthogonal traits depending on like what is the feature that you are talking about. For instance, if you talk about output guarantees, there are like again within malicious corruption you have security with abort, fairness, guaranteed output delivery. Similarly, it changes with respect to algebraic structure, the nature of computation, the nature of corruption, adversarial power, amount of corruption, and actually there are even more, which this is just a subset because now the research is even focusing on like okay, more and more variants of MPC in different orthogonal traits. And in this particular work we focus on this particular setting, like for the case of malicious corruption we focus on fairness guarantee. That means like if the adversary gets the output, then the honest parties also get the output. And we consider the computation over rings algebraic structure because that matches the typical hardware system, so it is more in line with the hardware system, and it is already shown like okay, the protocols over ring are faster than the protocols over field because of this new hardware support. And we have the computation in the pre-processing model. I will get back to this one in a later slide in detail. And the nature of corruption, we consider actually 2 corruptions. One is like the semi-honest corruption in one setting and the malicious corruption in another setting. and we are considering only computationally bounded adversary. So, everything is like within that setting, and we focus on honest majority in this particular protocol. So, before going into the details of the protocol, I thought of like giving some intro, and if you guys are like familiar, just let me know and we can like skip through them. So, I want to introduce this notion of function dependent preprocessing. So, by function dependent preprocessing, the idea is if you know the function that you are going to compute in advance, then you can actually preprocess a set of more amount of correlated materials compared to you do not know the function. Okay, so these are the two scenarios, right. So, I can like, if I do not know the function, what I can do is I can of course preprocess a set of correlated materials that are like very generic, for instance beaver triples and all. But if you know the function beforehand, you can utilize that knowledge to have more useful correlated materials that can help in the online phase. So, in this preprocessing, in this specific preprocessing model, again all the input independent computations are carried out in a preprocessing phase, where like they will basically like compute all these correlated materials, and they are all input independent, and the moment you get the input, that is the start of the online phase, where they use these materials to basically speed up the computations of the online phase, and this is a well known paradigm in the literature. And this is particularly useful in computation as a service scenarios. That means like for instance machine learning as a service or inference as a service, like there are so many service providers, right. So, they have like some specific set of tasks. So, the only thing that is going to change is the input. So, for instance like this is a VGG16 inference framework. So, the function to be computed is nothing but an inference on a VGG16. So, it is not changing at all. Every time the input keeps on changing. So, this is like one particular scenario where we can leverage this function dependent preprocessing. So, as I mentioned, it has two phases. So, the first phase is a preprocessing phase, which is like the input independent computation, and this is in general relatively slow and expensive. Okay. And the good thing about this one is like we can actually, there is no time limit in the sense like we can do this over a like larger span of time. For instance, these computations itself does not have to be like okay, all the parties that are the computation party, they have to come online and they have to do it together. For instance, you can even view this as like a mailbox kind of setup. Like I am a computational party, I will do my job, I will send the result or like that computation message to the next party, let us say over mail, and whenever the other party is available, okay, they will check their mailbox, get the value and proceed with the next computation and does this. So, that is why I said like this is not a time bound one. So, we can even like afford to have like more time in doing the pre-processing. And with this pre-processing materials in place, we can have like the input dependent computation, which is like the super fast one, which we mainly focus on. At least in our line of works, we focus on such a setting, because whenever we have this as a service, what we want is like the moment the user gives the input, we want the output to be computed as fast as possible. So, they can do all the pre-processing jobs if they want beforehand to make this particular online phase as fast as possible. So, that is the idea. So, in this particular line of work, at least my research, we started with this work called Astra. So, it is a 3-party one corruption setting. So, that is a 3-party honest majority protocol, and we consider both semi-honest and malicious in that setting. And I will like just list out the protocols. Okay, I mean there was Astra in 2019, and then like the 3-party protocol in the malicious setting was improved in Blaze, and then in Trident the corresponding 4-party maliciously secure protocol was proposed, and that is like the first 4-party maliciously secure protocol for the machine learning inference. And then like similarly there was another work called Flash, where the security was considered to be guaranteed output delivery, which is like the strongest setting compared to the fairness in Trident. And then there was Swift. So, these are like all like that comes one after the other. And essentially after that, like in 2021 there was ABY 2.0, where like the same paradigm was like used in a 2-party setting itself. And then in 2022 the cost of this 4-party protocols was further improved in a the work called Tetrad. Okay, and this list is not exhaustive, like I said, like there are even more function like papers or like research works that uses this notion of function dependent preprocessing. And in the literature, if you see, This idea of function dependent preprocessing goes back even to 2015, say Lindel's paper on multiparty garbling. Okay, that's the place where they started this one, but then like later Katz, I think Katz in one of the works they extended it to another garbling scheme. Then there was this work called turbo speeds, which Ben Ephraim et al. So they basically adapted this idea of this particular paradigm called masked evaluation, which we will see in the lecture. So they basically adapted that idea to the secret sharing domain, and then like there was even in 2018 there was this work of Gordon et al. In Asia Crypt where they considered a 4-party setting. So like I said, this list is not like complete. I just like only put the Astra line of families, Astra family of protocols here, because the protocols in the paper that I am going to present are based on this line of work. That's why I just put this. So the question is like, okay, this was like a very large line of work, right? So then like what next? We have like very efficient protocols over the span of like, okay, 3 years. So the question that we ask in this particular work is like, can we make these protocols more practical in real world scenarios? Okay. And then the question is like, okay, what do you mean by this more practical? Like where can this like notion be coming? So essentially we consider 3 bottlenecks, okay, in this work, which we found like, okay, these are the actual bottlenecks of deploying MPC in practice. So the first one is network heterogeneity. It's like usually we assume like, okay, these if there is a 4-party protocol, all the parties are connected with the same bandwidth and the same speed links, and they can like communicate at the same level. But in the real world, actually these connections are completely heterogeneous. So the bandwidth varies, the like connection speed varies. So all these things vary. So how to leverage this kind of heterogeneity in the actual network? The second one is the throughput, because most of these works are originated from an academic perspective. They focus on like, okay, some implementation which shows like, okay, the improvement over the prior works, okay, but they stop at that point. So the question is like, okay, is this actually the limit that they can push to, or like, okay, can we push more the throughput? So the throughput is basically the number of unit operations you can do like per unit time. So can we push the implementation, okay, so that we can use the state of the art optimizations within the implementation, like from a development perspective, can we implement these optimizations and increase the throughput even of the existing protocols as well as the protocols that we propose. And the third one is the computational complexity. Like I said, if you consider this line of works that I showed earlier in the previous slide, so all these works focused on like was focusing on reducing the number of communication, like reducing the number of elements that you need to communicate per multiplication, because that is kind of like a baseline for the efficiency of the MPC, underlying MPC protocol. So they keep on improving the like communication aspect, like the reducing the number of ring elements that they require per multiplication, and even like other protocols along the side, but not much focus was given on the computational complexity of these protocols. So the same protocol with the same communication, can we achieve better computation, okay, in terms of like computing the result? So going to this motivation in a bit more detail, like I said, the first one was the network heterogeneity. So these are actually the real world latency and bandwidth for various network settings, including LAN, MAN, and even a CMAN, and there are like 2 other, you have to refer to the paper for the exact details, but these are like obtained in various locations and even Amazon data centers, and even mixed is like, okay, some 2 entities are in one same location whereas the others are distributed like that. So you can see like the best and worst, they differ a lot. Even like you can see like, okay, some there is even a like difference of like 453% in terms of the latency, and for the bandwidth it's like around 1031% difference. So this basically depicts the heterogeneity in the underlying network. So the question here is, can the protocols prioritize the best links between the parties? Because like I said, some parties are well connected, whereas some others are not well connected. And in this scenario, we want to still run a 4-party protocol or like 3-party protocol. And how can we design so that we can actually like get rid of these particular bottlenecks? And the second one is the limitations of existing implementations in terms of throughput, because like I said, they are like, they haven't focused much on like increasing the throughput or like pushing to the limits. So if you see, everything is like I mean the maximum throughput is less than 1 million, I guess, gates. It's not even like the order of 10 power 5, sorry 10 power 6, but for instance in MP speeds you can get like in 3PC like around 19 million gates per second in terms of throughput. But this is like the like state of the art at this point. And what we observed is the open source frameworks often achieve less than 1% network saturation. So these are all like coming from a development perspective, not like the MPC protocol, but the MPC protocol design aids to basically achieve these or like overcome these bottlenecks. And the third one, as I mentioned, is the computational complexity. So if you see like in the literature, like at least for 3PC and 4PC, the communication cost of a scalar product is same as the communication cost of a multiplication. At least that's the state of the art. But when it comes to the computational cost, you can see like if the values are like actually this caption is wrong. Okay, I changed it, but I don't know where I changed it. So for like larger bandwidths, like they get like stabilized, but you can see a significant gap in terms of the computation for scalar product versus multiplication. So that is also like another gap, and that's because the scalar product implementation is not done in the right way, so that this gap is like completely minimized. So we focus on these kind of aspects with respect to the implementation perspective. So the CAN protocols be designed to minimize computational overhead. And coming to our contributions, so in this work we actually present two protocols. So one is focused on the 3-party semi-honest protocol, which basically improves upon all these features of Astra, which is the underlying 3-party protocol, and the other one is in the 4-party malicious setting. So these are the two mainly used settings, because like I said, 2, 3 and 4 they have their own like use cases. So 2-party mainly the current literature focuses on still on like the semi-honest setting, and the 3-party is where like they go to even like malicious and even semi-honest, but the 2-party semi-honest itself has some drawbacks which the 3-party can kind of overcome, okay, because you have an additional honest party, so you can leverage that honest parties to get rid of all these public key operations like OT and all those stuff. So that's why we consider the 3-party semi-honest protocol and the 4-party malicious protocol, because the most of the 4-party protocols are basically proposed in the malicious setting, as the corresponding 3-party malicious protocols are actually a bit expensive. So you probably need like a cut and choose technique or like zero knowledge proofs to ensure the correctness in the 3-party malicious setting. So that's why like community started focusing on 4-party malicious setting, where none of these things are needed, because you have like an additional honest party over there. So to summarize, like in this table we show like the number of operations and communications for a multiplication operation with respect to the state of the art works. So you can see like with respect to 3PC, we actually haven't improved the number of operations, okay, because the existing 3PC was, if you see the naive like Astra paper as such, for instance the number of multiplications was like 6, but you can do a naive optimization to reduce it to 5, okay. But the main reduction in the number of operations comes in the 4PC setting. So if you see like for performing a multiplication, if you consider the total number of operations across all the parties, so the state of the art like tetrad and all, like it requires 52 additions and 30 multiplications, whereas the 4PC protocol quad in this work requires only 25 additions and 12 multiplications, and this is a huge improvement, and it will actually reflect when it comes to the benchmarking. So this is like I mentioned, like the same, retaining the same communication cost, but doing things in a slightly different way so that the computation cost can be optimized. So that was one of the main goal. And on the communication front, what we focus is on like, okay, how many links among the parties that we can tolerate, like even if one connection goes down in terms of bandwidth or the network speed, whether our protocol gets affected or not, and that is basically by doing the careful design of the protocol. So we design the communication patterns in a specific manner so that at a time we probably need only like one solid connection, I mean like the connection between two parties to be the strongest one. Even if the other connections are getting deflected in terms of their performance, the protocol's performance will still not get affected. That's how the protocol design is being carried out. So a bit technical, like when coming to our protocols. So all these protocols use this idea of masked evaluation. So how many of you are aware of this concept of masked evaluation? Okay, one. So I think then the slides are good. So let me like quickly present this idea of masked evaluation from a three-party perspective. Okay, so this one is the simple replicated sharing in a three-party setting, where a value x is split into three parts, x1, x2 and x3, and the replicated sharing is nothing but each of the party will get 2 out of 3 shares. Okay, so they will be missing one share. So that's the simple replicated sharing. And the idea is for a multiplication, given the replicated sharing of x and another value y, you need to compute the replicated sharing of z. So that's the overall like protocol for the standard replicated sharing in the three-party setting. Now when it comes to masked evaluation, the idea is like that's why I said like this comes, the idea comes from a Gabling paper where they propose the idea of like external values and like masked values. So this comes over there. So what we do in masked evaluation is we define two additional variables in addition to the actual secret. So in addition to the actual secret x, we define two variables which is like the lambda x and mx. So the lambda x is called the mask because it is going to hide the secret, and the mx is called the masked value. Whatever be the secret masked with the mask, that's the masked value. So many masks, but that's it. So these lambda values are all random and they are independent of the computation, because like you said, you can choose random lambda values. The moment you choose lambda value and with given an x, then the mask is defined. So the m part is the input dependent part and the lambda part is the input independent part. So whatever be the computation that we require for the computation with respect to lambda can be done in the pre-processing, because they are not dependent on the input. So they can be random values. So in the pre-processing phase, the focus will be on all the computations that are related to lambda values. And once we have the pre-processing and once we have computed all the required details with respect to lambda, in the online phase we compute the mask value. So this is like the mask evaluation paradigm. So we have like two stages. And the secret sharing is also like slightly different in the sense like we basically have a replicated secret sharing of the lambda x itself. So in the earlier slide you saw how x is replicated shared. So similarly lambda x is having 3 parts and each one will have 2 out of the 3 parts, and the mask is given to all the parties. Okay, like I said, this is just a like illustrative example, but with respect to concrete protocols something can be changing. Even in our protocols there are like slight differences to it, and I will show in the like couple of slides later. But for instance, like okay, 2 of the parties can hold the mx and not the third one. So these are all like custom tailoring for the underlying protocols, but in general like the mask is given to all the parties. Okay, and we let's say like for the time being let's denote it in this double angle bracket. So the idea again, like the goal is very simple, like it's exactly the same. Given this kind of a sharing of the inputs x and y, compute this kind of a sharing for the output z. So I'll not go into the concrete details, but I'll like quickly glance through like how this idea works. So the idea is like okay, let's assume there is a magic box which distributed some random shares of this lambda z to the parties. Okay, so they have their pre-processing part set, okay, as per the shares of z. So the only thing is how to compute mz value, because they all need to get the mz value to complete the sharing, right? So mz is z plus lambda z as per the sharing semantic. And what is z? Z, because this is a multiplication gate, z has to be xy, and then we substitute x and y in terms of their mx and lambda x values. So just write out the expansion. So what you will be getting is this expression. So mz is mz can be computed using m and lambda values as mx my minus mx lambda y minus my lambda x plus lambda x lambda y plus lambda z. Okay. So, this is, so if the parties can compute this expression, then our job is done. But now if you see this part, every party can compute on its own, because they like possess both mx and my to begin with, right. Now this part, no, because they have mx in the clear, but they have only like parts of lambda y. Similarly, they have my in the clear, but only parts of lambda x. And this one, they don't even know how to compute, they don't have anything, okay, everything is in parts. And this one, they have the shares, lambda z1, lambda z2 and lambda z3. So the idea here is the parties are going to compute some additive shares of this mz, and then they are going to exchange, so that everyone gets. So whatever the party can compute, for instance, this party can compute mx times lambda y1. Similarly, other party can compute mx times lambda y2 and mx times lambda y3. So if they exchange and add, that will be mx times lambda y. And the problematic one is this one, the lambda x lambda y term, because that's again like it goes in circle, like that's another multiplication, right, that we need, because lambda x is secret shared among the parties, lambda y is secret shared among the parties, but in replicated sharing format, and they need to compute this one, and this is exactly the pre-processing part of a multiplication. Whatever they do to compute the shares, additive shares or like replicated shares of this term is the pre-processing part. And I am not going to the details of the pre-processing, because this keeps on changing with respect to the protocol, how you instantiate the pre-processing and all. Now coming to our protocol, one of the main change, because we want to have these features like, okay, we want to minimize the computation and all. So the core idea at a very high level is called oblivious error correction. So it is essentially viewing the same problem of computing this mz, but in a slightly different manner. To show that, I can show you like the example with respect to the 3PC. So this is like a 3PC sharing of Astra protocol, okay, the one on the top, where P0 has lambda x1 and lambda x2, P1 has mx and lambda x1, and P2 has mx and lambda x2, okay, simple one. And the definitions are lambda x is nothing but lambda x1 plus lambda x2, and mx is x plus lambda x. Now in the corresponding 3PC protocol of ours, which is like trio, we slightly change it, in the sense like P0 still holds lambda x1 and lambda x2, but P1 instead of holding mx, it will only hold mx2, okay, and similarly P2 holds only mx1. If you see, these are equivalent in terms of the information that they contain, but the way they represent is actually helping in doing the computations further, because in this kind of a scenario, every time the party has to store the mx, but in their next subsequent computation they have to kind of like, okay, recompute this mx1 and mx2 from that one. So that's what the core change is with respect to the 3-party protocol. So it's basically like you redefine the shares such that the shares hold the sufficient amount of information, and we can reuse the shares at the maximum. So instead of like, okay, holding some like added value in the memory, I will hold the individual value that is required for me, so that I don't have to do this extra task of like, okay, deriving mx1 for the subsequent computation. Just one change with respect to 3PC. And similarly with respect to 4PC, like this was the sharing in tetrad, which was like the NDSS 2022 paper, where 3 parties holds the value mx in the clear, and the lambda x value is like kind of like replicated shared among the parties, okay. So if you see P0, P1 and P2, they have a replicated sharing of lambda x value, and P3 holds the full 3 shares. So this was the sharing semantics in tetrad. Now the same amount of information can be conveyed in a slightly different manner by using slightly different way of expressing, where we have instead of one mx value, we will have 2 mx values, okay. There is an mx and an mx star, and they are like actually related like this. So you have basically 2 equations like with respect to the same secret itself. So there are 2 correlations, and this actually helps in drastically cutting down the computational cost of the underlying multiplication protocols. Of course, we have to come up with the corresponding design, but I am just trying to give you the intuition behind like the major change with respect to these 2 protocols. And the next slide will look a bit large, but again you do not have to like follow this protocol. So, this is the 3-party protocol. All I want to show here is like again the intuitive part of it. So, how the 3-party protocol is going to work is, in the pre-processing, this P0 who is having this lambda x1 and lambda x2, it is going to compute some value using its available set of values like the lambda values. Okay, it will, let us denote it as like M0, whatever P0 can compute in the pre-processing. Now, in the online, they are going to like P1 and P2 are going to compute some values based on what they hold. Okay, and the logic here is, whatever P1 is going to send to P2 in the online, the goal of that message is for P2 to get the correct message. Okay, is this confusing? Slightly. So, what I am saying is, here the way in which we are designing the protocol is like P2 can compute some value in the online using the values that it possesses. Okay, and we want P2 to correctly compute its share. So, we will see what exactly is the missing piece of information, and we call that piece as like kind of an error, because that is an extra information that it has because of the values that it possesses. So, whatever be the error, we use the messages from, I mean the messages from the other parties are kind of crafted in such a way that this error can be mitigated. Okay, similar for the other party. So, this is the design principle that is the major change with respect to the existing line of protocols, because in the existing line of protocols all we were focusing is on like computing the additive sharing of that particular expression of mz. So, how to efficiently compute an additive sharing of that one, and then they exchange, that was the way. But here these are like, okay, we go further down into the expression and write out all the terms. For instance, in that previous expression that I have shown, I have simply given like mx times lambda y, but in this kind of a scenario, like we write out all the terms. Okay, so it will be like, okay, mx times lambda x1 plus mx times, sorry, my times lambda x2 plus, and like that we write out everything, and then we see like, okay, what this party can compute and what this party needs. So, there will be a difference, whatever be the difference we call that as an error, and we craft the other messages in such a way that the error can be mitigated. So, that is the main difference with respect to the existing line of protocols. Now it is like the interesting part only, because the protocol part is done. So, as a result of this particular project, we have this HP MPC framework. So, this is like the high performance MPC framework. So, this is like an open source MPC library, and it is available here in this QR code, and this is the URL. So, it is an open source C++ framework implementing both existing MPC protocols and our new ones. So, it not only implements these two protocols, it has more in the framework, and this is designed for lightweight performance with hardware acceleration techniques, because like I said, one of the major contribution of our work is basically focusing on the development perspective also. In addition to coming up with the theoretical improvements in terms of the protocol design, we focus on how much we can push from a development perspective, and this is like done single handedly by this my collaborator Christopher, which I showed in the first slide. So, it is his marvelous work, and it basically like uses hardware acceleration techniques to saturate available network resources, and it is open sourced under MIT license. And if you see, like currently it supports this many variants of the protocols, like 12 protocol variants. Why I call variants is like, for instance, in quad itself, like we have 3 variants depending on the network and all, like if it is designed for a heterogeneous network and all. I refer to the paper for more details of it, but currently it supports this many protocol implementations. And coming to the implementation and benchmarking, the environment is like we have the nodes connected with a 25 gigabit duplex network, and the nodes are equipped with 32 core ePIYC 7543 processors, and we have the like local round trip latency of 0.3 milliseconds. And in the implementation, we have like incorporated all these optimizations of bit slicing, vectorization, multiprocessing, vector AES instructions, and even adjustable message buffering. I will show the impact of buffering in a moment, I guess. And for doing all this bit slicing, we use the header files by this Usuba bit slicing compiler. So these slides like will show the general optimizations. So these are not like restricted to our protocols like our 3-party and 4-party protocols, but these are some things that are optimizations from a development perspective. So we can even like observe improvements in the existing protocols as well. So this is like when we have the bit slicing and vectorization, like we can have like a large throughput compared to the existing implementation. So that I forgot to add the reference line of the other one, like which was the previous one, but believe me, these are like very large throughputs in numbers. And the next one is the network communication. So this is where buffering takes a role. So essentially from a protocol perspective, it's like, okay, I compute some message and I send to the other party, right? But when it comes to the implementation, sometimes you can actually collect a set of messages and then send in one shot instead of like continuously sending for each and everything, okay? For instance, like all the layers in the network and all. So we use this buffering technique over there, and we found that if we keep the buffer size to be in between 0.3 megabyte and 3 megabyte, we can approximately get like more than 50 times in terms of the throughput, because we are not continuously like sending, but instead like we buffer and send. And the other one is called split roles idea. So the split roles idea is because, like I said, in the protocols, for instance, in the 3-party protocol, this P0 is mainly like in the pre-processing phase. It does this pre-processing job and then like shares to one party. And the P1 and P2 are the main parties who computes, like does most of the online computation. So what we can do is take another instance and switch their roles. So in another instance, this P1 will be the P0 and P0 and P2 will be the online parties, and we can have another instance. So we can basically balance the load across the multiple instances. So that's the idea of split roles. So these are the throughputs with respect to the AND gates computation without the split rules. And when we have split roles, you can see like the throughput increases very drastically, okay? Because like I said, the other case when we don't have split roles, several of the channels are like underutilized. So we want to basically increase the throughput. And these are some numbers with respect to AES benchmark, and we can have like millions of AES blocks per second in the current implementation. Now with respect to the implementation, there are some particular settings which we specifically focused in this paper, as I mentioned in the beginning. So one is like the network heterogeneity. So here we want to see how this new design helps in improving the like efficiency over these settings. So there are 3 kind of constraint workloads that are considered in this work. One is like the latency constraint, one is bandwidth, and one is compute. So in latency constraint, what we did is like, okay, for a 4-party setting, there are like 6 links among the parties, right? Because it's 4 parties. We cut the latency of 5 out of the 6 links, okay? So among all the 6 links, we reduce the latency in 5 of them and see how it affects the protocol's performance. So you can see like because of the design in which, like because of this new design, like I said, it's mainly like one active link which is required all the time. So even if the other 5 are affected, the protocol's performance are not affected. So that is basically this green line for the quad base 4PC and all. And similarly for analyzing the impact of this bandwidth restriction, we cut 2/3 of all the links, like we reduce the bandwidth of 2/3 of all the links, and we can see like, okay, the protocol's throughput was not affected in our protocols, whereas the others are affected. So it needs like 10,000 megabits per second to reach the same throughput. And this one is basically like we have large vectors, and we basically evaluated the runtime for scalar dot products, okay? And because of this improvement in the computation, we can see like that gets reflected here. So these are like the 3 different aspects where our protocols excels, and correspondingly like we benchmark again the performance of AES itself in these constraint settings, considering all these like constraints together. And we can see like with respect to the previous one, for instance, like the existing replicated in a like for instance even in a WAN 1 setting, it can only have like 20, close to 20 million AES per second, whereas TII can achieve like 45. Similarly, with respect to Fantastic 4, which was like the 4 PC work, from 8 to 34. So that's like a massive improvement in terms of the throughput. Yeah, so that's the end of the talk.